improperly connected ground rods pose a safety risk. The correct method involves connecting the ground rods to the ground clamps in a daisy chain fashion. This means that one ground rod should be connected to the clamp, and then the next ground rod should be connected to the same clamp, and so on. Make sure the ground clamps are tightened securely to ensure good electrical connection. Proper grounding is essential for the safe operation of electrical systems. Grounding provides a low-resistance path to earth for electrical current, which helps protect against electrical shocks and fires. Without proper grounding, electricity could travel through a person's body to the ground, creating a dangerous situation. To properly ground the electrical panels, 1. Disconnect the power to the panels. 2. Remove the ground clamps from the ground rods. 3. Connect the ground rods together in a daisy chain fashion. 4. Reinstall the ground clamps on the ground rods. 5. Tighten the ground clamps securely. 6. Reconnect the power to the panels. The ground rods should be at least 8 feet long and driven into the ground to a depth of at least 6 feet. Also, the ground rods should be spaced at least 6 feet apart. If you are not comfortable working with electricity, it is best to hire a qualified electrician to ground the panels. Grounding is a critical safety measure in any electrical system. Its primary function is to provide a low impedance path for fault current to return to the source, which facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses. This rapid response minimizes the duration of a fault, reducing the risk of electrical shock and fire. Grounding also helps stabilize voltage levels during normal operation, preventing voltage surges that can damage sensitive electronic equipment. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding electrical systems. These guidelines cover various aspects, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the requirements for grounding different types of equipment. Adhering to these guidelines is essential for ensuring a safe and reliable electrical system. Grounding electrodes, such as ground rods, are a crucial part of the grounding system. They provide a physical connection to the earth, allowing fault current to dissipate safely. The NEC specifies the minimum requirements for grounding electrodes, including their size, material, and installation depth. Ground rods must be made of approved materials such as copper or galvanized steel and must be at least 8 feet long. They must be driven into the ground to a depth of at least 8 feet unless rock bottom is encountered. The spacing between ground rods is also important. The NEC requires that ground rods be spaced at least 6 feet apart to ensure that they provide adequate grounding. When multiple ground rods are used, they should be bonded together with a grounding electrode conductor to create a low impedance path for fault current. Grounding electrode conductors are used to connect the grounding electrodes to the electrical system. These conductors must be sized according to the NEC tables based on the size of the service entrance conductors. The grounding electrode conductor must be made of copper or aluminum and must be protected from physical damage. Equipment grounding conductors are used to ground non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and motor frames. These conductors provide a path for fault current to return to the source, preventing voltage from building up on the metal parts. Equipment grounding conductors must be sized according to the NEC tables based on the size of the circuit conductors. The NEC also requires that equipment grounding conductors be installed in the same raceway or cable as the circuit conductors. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to equalize voltage potentials and prevent voltage differences that can cause electrical shock. The NEC requires that all metal parts of an electrical system, including enclosures, raceways, and piping, be bonded together. Ground fault circuit interrupters, or GFCIs, are devices that protect against electrical shock by detecting ground faults. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs quickly interrupt the circuit when a ground fault is detected, preventing serious injury or death. The NEC requires GFCIs to be installed in certain locations, such as bathrooms, kitchens, and outdoor areas, where the risk of electrical shock is higher. Surge protective devices, or SPDs, are devices that protect against voltage surges. Voltage surges can be caused by lightning strikes, power line switching, or other events. SPD divert the surge current to ground, protecting sensitive electronic equipment from damage. The NEC recommends the use of SPD in all electrical systems to protect against voltage surges. Regular inspection and testing of the grounding system is essential for ensuring its effectiveness. The NEC requires that grounding systems be inspected and tested periodically to verify that they are properly installed and functioning correctly. Grounding electrode resistance testing is a common method for evaluating the effectiveness of the grounding system. This test measures the resistance between the grounding electrodes and earth. A low resistance indicates a good grounding system, while a high resistance indicates a problem. If the grounding system is not functioning correctly, it should be repaired or replaced by a qualified electrician. When working with electrical systems, it is important to always follow safe work practices. Always disconnect the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as rubber gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. The purpose of electrical grounding is to provide a safe path for electrical current in the event of a fault. This helps to protect people from electric shock and to prevent fires. The NEC specifies the requirements for electrical grounding in Article 250. There are two main types of electrical grounding: system grounding and equipment grounding. System grounding is the intentional connection of a current-carrying conductor to earth. This is typically done at the service entrance of a building. Equipment grounding is the connection of non-current carrying metal parts of electrical equipment to earth. This includes things like metal enclosures, raceways, and motor frames. The purpose of system grounding is to stabilize the voltage of the electrical system and to provide a path for fault current to flow back to the source. The purpose of equipment grounding is to provide a low impedance path for fault current to flow back to the source, which will cause the overcurrent protective device to trip and energize the circuit. There are several different methods of system grounding, including solidly grounded, impedance grounded, and ungrounded systems. Solidly grounded systems are the most common type of system grounding. In a solidly grounded system, the neutral conductor is connected directly to earth. Impedance grounded systems use a resistor or reactor to limit the amount of current that can flow to ground in the event of a fault. Ungrounded systems do not have a direct connection to earth. These systems are typically used in industrial applications where a high degree of reliability is required. There are also several different methods of equipment grounding, including using a grounding conductor, using a metal raceway, and using a combination of both. A grounding conductor is a wire that is used to connect the non-current carrying metal parts of electrical equipment to earth. A metal raceway is a metallic enclosure that is used to protect electrical conductors. Metal raceways can also be used as an equipment grounding conductor. The NEC specifies the size of the grounding conductors and the type of connections that are required for equipment grounding. The NEC also specifies the requirements for grounding electrodes. A grounding electrode is a conductor that is used to connect the electrical system to earth. There are several different types of grounding electrodes, including ground rods, ground plates, and metal water pipes. Ground rods are the most common type of grounding electrode. Ground rods must be at least 8 feet long and must be driven into the ground to a depth of at least 8 feet. Ground plates are metal plates that are buried in the ground. Metal water pipes can also be used as grounding electrodes, but they must meet certain requirements. The NEC requires that all electrical systems be grounded in accordance with the requirements of Article 250. Proper grounding is essential for the safety of people and property. The function of a grounding system extends beyond simply providing a path for fault currents. It also plays a vital role in minimizing electrical noise and interference, which can disrupt the operation of sensitive electronic equipment. A well-designed grounding system helps to maintain a stable voltage reference, ensuring that electronic devices operate reliably. In industrial settings, where equipment is often subjected to harsh environmental conditions, a robust grounding system is crucial for preventing corrosion and extending the lifespan of electrical equipment. Corrosion can occur when dissimilar metals are in contact with each other in the presence of moisture, creating a galvanic cell. A properly grounded system helps to equalize the electrical potential between different metal parts, minimizing the risk of corrosion. Furthermore, grounding is essential for protecting against static electricity buildup. Static electricity can accumulate on surfaces due to friction or induction, and if discharged suddenly, it can damage electronic components or ignite flammable materials. A grounding system provides a path for static electricity to dissipate safely, preventing these hazards. The effectiveness of a grounding system depends on several factors, including the quality of the grounding electrodes, the size and type of grounding conductors, and the integrity of the connections. Regular inspection and maintenance are necessary to ensure that the grounding system continues to function properly over time. Visual inspections can help identify signs of corrosion, loose connections, or physical damage. Electrical testing, such as ground resistance testing, can verify that the grounding system is providing a low impedance path to earth. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve the required grounding resistance. Soil resistivity is a measure of how well the soil conducts electricity. High soil resistivity can make it difficult to establish a good ground connection. The NEC provides guidance on how to improve grounding in areas with high soil resistivity. This may involve using longer ground rods, installing chemical ground rods, or using a ground grid. Chemical ground rods contain chemicals that leach into the soil, reducing the soil resistivity and improving the ground connection. A ground grid is a network of interconnected conductors buried in the ground. Ground grids are typically used in large electrical substations or industrial facilities to provide a low-impedance ground path over a wide area. In addition to grounding for safety, there is also grounding for lightning protection. Lightning protection systems are designed to protect buildings and equipment from lightning strikes. These systems typically consist of air terminals, down conductors, and grounding electrodes. Air terminals are installed on the roof of the building to intercept lightning strikes. Down conductors are used to carry the lightning current from the air terminals to the grounding electrodes. Grounding electrodes provide a path for the lightning current to dissipate safely into the earth. The NEC provides specific requirements for lightning protection systems in Article 250. The design and installation of lightning protection systems should be performed by qualified professionals. The selection of appropriate grounding methods and materials depends on the specific application and the local site conditions. A thorough understanding of the NEC requirements and best practices is essential for ensuring a safe and effective grounding system. Consulting with a qualified electrical engineer or electrician can help ensure that the grounding system is properly designed and installed. Grounding is not a one-size-fits-all solution. The best grounding method will vary depending on the type of electrical system, the soil conditions, and the local regulations. It is important to carefully consider all of these factors when designing a grounding system. One common misconception about grounding is that it is only necessary for large electrical systems. In reality, grounding is important for all electrical systems, regardless of size. Even small electrical systems can pose a safety hazard if they are not properly grounded. Another misconception is that grounding is a substitute for overcurrent protection. Grounding and overcurrent protection are two separate safety measures that work together to protect people and property from electrical hazards. Grounding provides a path for fault current to flow back to the source, which will cause the overcurrent protective device to trip and de-energize the circuit. Overcurrent protection protects against overloads and short circuits, which can cause fires. It is important to have both grounding and overcurrent protection in place to ensure a safe electrical system. When installing a grounding system, it is important to follow the manufacturer's instructions carefully. The manufacturer's instructions will provide specific guidance on how to install the grounding electrodes, connect the grounding conductors, and test the grounding system. Failure to follow the manufacturer's instructions can result in an ineffective grounding system. Regular maintenance of the grounding system is also important. The grounding electrodes should be inspected periodically for corrosion and damage. The grounding conductors should be checked for loose connections. The grounding system should be tested periodically to verify that it is still providing a lower impedance path to earth. Any problems with the grounding system should be corrected promptly. Grounding is a critical aspect of electrical safety. By following the NEC requirements and best practices, you can ensure that your electrical system is properly grounded and that people and property are protected from electrical hazards. Remember to always consult with a qualified electrical professional for any electrical work, especially when it comes to grounding systems. They have the knowledge and experience to ensure that the system is installed correctly and meets all applicable safety standards.